Hello, myself Priyesh Kumar Pandey, faculty of GIC campus. Today I discuss the network theorem. We discuss here different types of theorem. First we discuss Thevenin's theorem, second Norton's theorem, third maximum power theorem, fourth superposition theorem, and fifth Delign's theorem. Different types of theorem we discuss here and applications of this theorem in future I will also discuss. So first of all we discuss what is a Thevenin's theorem and where it is used. So first of all we discuss Thevenin's theorem. First of all we draw a circuit in which we find a Thevenin's voltage, Thevenin's resistance. After drawing a Thevenin's equivalent circuit, we find a overall current. First of all, we draw a circuit. First, we draw a circuit. Suppose 10 volt, 2 ohm resistance here, 4 ohm resistance, here 3 ohm resistance, here 5 ohm resistance, here 2 ohm, and here 2 ohm resistance. And find Thevenin voltage find Thevenin equivalent circuit across we take following step to calculate Thevenin's voltage, Thevenin's resistance and overall current across. These are the normal circuit. We have find Thevenin's voltage, Thevenin's resistance across AB. After calculating Thevenin's voltage and Thevenin's resistance across AB, then we draw a Thevenin's equivalent circuit finally. The following step we have used for calculating Thevenin's voltage. First, open circuit across AB. Second, find Thevenin's voltage or open circuit voltage across third, find Thevenin's resistance across fourth row Thevenin equivalent and fifth find current to load. These are the steps to find, to draw a equivalent Thevenin equivalent circuit. First, find Thevenin's voltage, open circuit voltage across AB. Second, we find Thevenin's resistance across AB. We again draw Thevenin's equivalent circuit. And fifth is find current through a load. First of all, find Thevenin's resistance across AB. Open circuit first, and find EOC equals to equals to 80. Apply KCL at a node suppose this is my node A, this is my current I, here I1, here. When we apply KCL at a node A, then I equals to I1 plus I2. So 10 minus VA divided by 2 equals to VA upon 4 divided by VA upon, because here I equals to, because this side open circuit and circuit is open and then no current is flow through this circuit. So these are the first equations. After calculating we found 10 minus VA equals to V, means 40 equals to 7 VA and VA equals to by voltage at a node A equals to 10 40 divided by 7. These are the voltage calculate at that point. Put this voltage in equation 1. So 10 minus VA upon 2 VA upon 4 plus I2. So I2 equals to 10 minus VA upon 2 minus VA upon 4. So I2 equals to 2 10 minus VA divided by 4. So I2 equals to 20 minus 2 VA minus VA divided by 4. So I2 equals to 20 minus 3 VA upon 4. So I2 equals to 20 minus 3 into 40 by 7. So I2 equals to 140 minus 120 divided by 4. So I2 equals to 20 divided by 7. These are the current that flow through a 5 ohm resistor. After calculating I2, we have found VO. Since here suppose V, voltage V, this voltage V equals to I into 2 minus VOC equals to, since A and B is open circuited, so I equals to 0. So put here 0 into 2 equals to VOC, VOC equals to, so V equals to VOC and V equals to 5 into I2 and 5 to 20 by 7 equals to 100 by we found VOC or VTH equals to 100 by 7. These are the Thevenin's voltage 100 by 7. Again, for calculating Thevenin's resistance, for voltage source is short circuited and current source is open circuited. Step to find a Thevenin's resistance. First, check which source is connected with circuit, voltage source is connected or current source. Here the voltage source is connected with circuit, so we short circuited first voltage source, then we calculate Thevenin's resistance across AB. Here first draw circuit, ten volt, here volt, volt, 3 ohm, here 5 ohm, 2 ohm and 2 ohm, and for calculating Thevenin's resistance across AB, when first and short circuit here. For calculating Thevenin's resistance, first we check which source is connected, current source or voltage source to the circuit. Here voltage source is short connected with circuit, so we short circuited the voltage source and calculate Thevenin's resistance across a RB, across a AB. These are the Thevenin's resistance are P. Here A and B are in parallel, and this 2 and 4 ohm, sorry, A and B not 2 and 4 ohm connected in parallel and series with 3 ohms, but this 2 and 4 ohm connected with 3 ohm in series but parallel with 5 ohm. So following step we have to we have to use to calculate a Thevenin's resistance. Here 2 and 4 ohm are in parallel. So R equivalent 1 equals to 2 into 4 divided by 2 plus, because in parallel R1 into R2 divided by R1 plus of R of 2. So R equivalent 1 equals to 8 by 6. So here 4 by 3. It means R equivalent 1 equals to 1.33. These are connected. These are R equivalent 1. This value is 1.33. This 3 ohm and this 1.33 ohm are in series. So R equivalent 2 equals to R equivalent 1 plus R. So R equivalent 2 equals to 1.33 plus R equivalent 2 equals to 4.3. R equivalent 2 equals to 4.33 ohm. Now this 4.33 ohm connected with 5 ohm in parallel. R equivalent 2 equals to 4. R equivalent 3 equals to R equivalent 2 into 5 divided by R equivalent 2 plus 5. So R equivalent 2 is equal to 4.33 into 5 divided by 4.33 plus 5. So finally R equivalent 3 to 3. So R equivalent 3 equals to 2, 6, 205 divided by 8 equals to 2.5 ohm approx. This R equivalent 3, so RTH is equals to 2 plus 2.5, so RTH equals to 4.5, RTH equals to 4.5. Here calculate Thevenin's voltage is equals to 14.16 volt and RTH equals to 4.5. Here VOC is equal to Thevenin's voltage and RTH equals to Thevenin's resistance. After calculating Thevenin's voltage and Thevenin's resistance, we know easily Thevenin's equivalent circuit. In Thevenin's equivalent circuit, Thevenin's voltage and Thevenin's resistance are connected in series with load resistance. So, we draw a Thevenin's equivalent circuit. These are the voltage, is called VOC or VTH. Here we draw RTH, here draw R. These are called Thevenin equivalent circuit. This Thevenin's equivalent circuit connected with load resistance in series. The value of this load resistance is 2. Here VTH is equals to 14.11 and RTH equals to 4.5. So finally we calculate current through a load resistance RL. So apply KVL. I equals to P by RTH plus RL. So V equals to 14.11, RTH equals to 4.5 and load resistance equals to I equals to 14.11 divided by 6.5. It means 2.11 ampere current flow through this load resistance RL. Here we discuss Thevenin's theorem. Thevenin's theorem applicable for linear bidirectional elements. It is not applicable for non-linear element. Non-linear element means it is not applicable for power, because power equals to V into I and P equals to G by R, P equals to by. The graph between power and voltage is non-linear, so Thevenin's voltage is not applicable for calculating a power. These are the demerits of this theorem. This theorem is only applicable for linear bidirectional element, not a non-linear element. So, after discussing Thevenin's theorem, I will discuss Norton's theorem in next class. I will take a next class in 1 October, 1st October. So, all the students present 1st October. Thank you very much. Thank you for all listening my voice. Please subscribe, like this video.